Yeah, thank you for inviting us and letting us speak at your seminar. Today, you might see from the slides, we would like to talk a bit about how to scale a training. I will start very small. I will try to show you an example of what happens when you do a training on one GPU, just to give some motivation of why it's relevant to know a little bit of the hardware that you're using and the software that you're using and what you can do at your own advantage to make the training go faster. Faster is a very broad term. You might interpret it in different ways, like going faster, converging faster with your model so that you have to do less steps to achieve a good accuracy, or go faster in the sense that every step of the training is faster because you optimize your code, or all kind of things. Bit of agenda. I structured it in a way that it can be interactive. So we'll have an introduction with an example, and I have a few slides that are a sort of summary of of everything. And from there, if you want to ask me any question, I have a lot of slides after that we can take bits and pieces to depending what you're interested into. Yeah. So please ask any question and try to keep it interactive. I'm not sure I see the chat in Zoom, but maybe if someone has
I'll have a look.
Just shout and we will try to answer the question. I mean, you have already introduced me, but yeah, nice to meet you. I'm Andrea. Now I'm based in Bologna. I work for NVIDIA. Let's say my main customer that I support is Cineca, that is the Italian supercomputing center. And also I work in a group of solution architects that support academic researchers. This group of people is called NVIDIA AI Technology Center. We are spread all around Europe and all around the world. And our job is to support researchers that want to use NVIDIA technology to publish, to prepare papers. So our goal essentially is to make sure that the trainings or inference or simulation that they run are done in the most efficient way so they can get the maximum out of this big cluster or even out of their workstation at home. So that in a way, we don't have papers only of the big companies that have a lot of compute, but we have also a lot of papers from universities that usually have great ideas and can help the innovation or improvement of and technology in general. Yeah, if you think that we can be helpful, there is Severin, that is our point of contact, or also Pallavi, that is also in Munich. They are here with me. We work in the same group at NVIDIA. I think you already know them because for sure Severin gave a talk. And yeah, so introduction, where are we? I put this slide just to show a little bit where we are at the moment. So essentially, if you think about NVIDIA, a key moment is for sure in 2005-06 when Ian Buck came out with CUDA. That made the GPU a programmable chip. So now we can use it to do many different things. And it turns out it works pretty well for GEM, so matrix multiplication. And one use case of matrix multiplication is AI. Essentially, most of the time when you run inference or training with an LLM, you spend it doing matrix multiplication. So that's why it worked pretty well. And 2012, we had ImageNet with AlexNet, and there it came out to the world, let's say. And then 2016, NVIDIA created the first DGX, so a server that is thought to do AI. And then from there, it grew and grew even more. Another interesting thing is that NVIDIA acquired Mellanox in 2019. We have a company that does networking. You might think, why a company that does networking? Because it turns out that for AI it's extremely important to have a good, fast, high bandwidth, low latency network, because otherwise you cannot parallelize your code and so on and so forth. Yes, this cluster uses a lot of power, but one thing we like to say is that power is not the same thing as energy. So if your simulation gets much shorter, even if you consume more power, it might be that you save a lot of energy. So that's why we tend to use GPUs for many different applications. And then one last thing before I try to show you the demo, if the cluster supports me, is that we are in a time where the compute can help us to achieve better results. So there is this slide that maybe you even already saw because it's quite widely used at NVIDIA, where we show that when you train your foundational model, people found out that there are scaling laws that tell you that data size, the amount of data, the model size, and the compute that you have at your own disposal go together. Like if you increase one, you should also increase the other two. We sort of have a better model. And then here you can see that it even grows on top because of post-training scaling. So what we noticed recently, for example, with reinforcement learning is that this model can improve a lot more if we keep training them to do what we want to do. And finally, the newest thing that was added is the test time scaling. So we give time to this model to reason, they will give us hopefully better results. So yeah, this is more or less the three type of scaling that we have. If you are interested in knowing more, I have slides about the pre-training. So if you are interested after, let me know. I can spend a bit of time there. But now, before we go into the rest of the slides, I would like to start with a little demo. Let me like so what happens now? I will show you a very simple, I don't want to say stupid, but easy example of something that can go bad very quickly. I'm going to log in into the Leonardo cluster at Cineca. This is the, let's say, the tier 0 cluster of Italy. So it's the biggest one that we have at the moment. Let's not say that it's old, but it's already in production for like 3-4 years. So what you have is 3,500 more or less nodes with 4 A100 GPUs. So it's not the latest, but it does the job pretty well. There is also a partition with CPUs only for people that need just, let's say, more classic simulation. And the network is InfiniBand. So you have a very high-speed connection from each GPU to each other GPU. This is pretty cool if you run AI training because it can communicate very fast. And yeah, so let me see now if I'm able to start my container. So now I'm doing something that you should not do, maybe, because I'm using the debug queue. I'm using a debug queue because we will need this for 10 minutes, and I want to have quick access to a compute node. If you've never seen how, have you ever used Slurm to run an experiment?
Much.
Yes. So, but I saw someone saying no. So this is a command that says srun. It's a command that allows you to start an interactive session, like if you are opening a terminal on the compute node. So like if you are using a computer with a GPU, for example. I ask 30 minutes, one node, one task. So let's say one job sort of on one GPU, on the partition that has the GPU, because I just said we have two partitions. Then there is my account where this time of compute is going to be built. and then a bash. Here you can see that I was on the login, and now I am on the compute node because the address changed. If I call NVIDIA SMI, I can see the GPU. Then what I'm going to do is to start Singularity. So I have my container with the environment ready. So I didn't tell probably which experiment I'm going to run, but I'm basically taking the code from PyTorch of the ImageNet example, a very classic computer vision training for classification. And so what I will need to pass to my container is the folder where the data is stored. The cluster has already the datasets downloaded for me, so I'm happy like this. And then I go to the code. Is here. This is just a wget of the code from the repo. And the changes I did are the following. I just edited the code to add a part where I compute the time that it takes to process a batch. So just to understand how fast it goes, an iteration of training. And I also added the option to use BF16 precision. So I can run this script classical way with FP32 precision, numerical precision, or BF16. Why I'm doing this? Because I want the training to go faster. Because the A100 GPU has the tensor cores that can accelerate to FP16 the training. So what I want to show you is compare how this script works if I find the commands to run it. So we start without the BF16. This should be the original command. Now I don't remember if this batch size fits, probably not. We can see that very quickly. So it goes out of memory. I think I need less images. This works. So this should work now because we don't have. What I need to do in parallel is to open another connection to the cluster. To show you the memory utilization. This is the node where I'm running. I'm just connecting to it. So now we have our training running. It says that we are processing around 500 images per second. It needs to have around 50 gigabytes of VRAM to store model activation, gradients, optimizer, everything. And the GPU utilization is pretty good. What I want to show next in this very simple example is that what happens if we use lower precision to speed up our training? Does it actually go faster? Does it work easily out of the box, or do we need to be careful? So, good thing is that I'm using BF16 and not FP16. Why I do that? Google came up with BF16 because they keep the same dynamic range, so maximum and minimum number that you can represent the same as FP32, but the precision will be lower. You will have less number in that range that you can represent. They did that because this way the gradients are more stable. You don't get out of range numbers. Otherwise, you might have problems when you learn the model. What I'm going to do here is to add BF16 and now see if the training goes. By the way, I think generally speaking in LLMs nowadays, everybody uses FP16 or BF16. I don't think, maybe in computer vision, sorry, people still use this FP32, but it's not so widely used. So what happens? Now we have basically doubled the images per second that you can process. We have half of the memory, more or less, because we are exploiting the fact that all the model, the weights, the activation, the gradients, it's in BF16. What you see here that the utilization is quite bad. It keeps going up and down. And we can see it also here because one iteration we have 500, one iteration we have 1000, so it keeps going up and down. Have you ever found a situation like this in your trainings? How can we get around this?
There could be multiple things, but the biggest problem was usually loading the data because it was too slow for the processing unit, and then were these bottlenecks.
Yeah, that's a very good point. We can check our data. So, for example, here, so I didn't explain you the commands here properly, so I'm sorry, but you have, I'm calling the model, I'm initializing a transformer model, the VIT. This is the number of workers of our data loader. This is the batch size. So actually one thing we can check very quickly is if we give more workers to our data loader, does it help us? So in this script that is written in PyTorch, the way it creates the data loader is that there is a process that is the data loader with the worker that loads the data. And if we set more workers, it will spawn sub-processes. Each of them will load a batch of data for us and get it ready to give it to the GPU. If we do like this, now I went from 4 to 8. We can check how the training goes. Now it seems to be better because it's more consistent. So it means that in this case, lowering the precision means that the GPU is hungry for data. Is starving, they say in. And also here the utilization is better. So yeah. Another thing we can fix now is that we have a very low memory occupation of the GPU. So the next fix is that increase the batch size. So this is just a quick example of things that can go wrong, even in a very easy case. So that's why I'm trying to use this as a motivation of why I'm doing this talk to you, to inspire you maybe to give a look when you are running your training at some metrics like, I don't know, token per second you're processing or other type of metrics. And another thing that might happen now is that if we have very large batch size, the training will not convert so nicely because we are further and further from the assumption of stochastic gradient descent. And so for that, there are special optimizer that can help you to still converge well. So are there any questions on this example? Was it clear what I tried to do? Essentially, I put the GPU in a situation where it was starving for data. And so what I want you to take away is simply that you have to be careful when you run a training so to have it utilized well.
But basically, by changing the accuracy of your training process, you did not change the accuracy of the data you were loading. You were still loading the same
I was loading
volume, because usually if you go to lower precision, maybe also input data which you load goes to.
So the data on the hard disk, I didn't change it. The same.
So the amount of time.
The thing change is that when I load the data, I convert it to BF16.
So the amount of the time for loading the data was the same, but executing the code.
Yeah, and that's true, and that's also one motivation that I used to talk about how you efficiently store on your hard disk the data, so that the I/O is utilized at the best for your model. So very often, also when I was a PhD, I had these big data sets in folder, not encrypted, not packaged in a tar file, for example. And that's extremely bad for the hard disk or for the I/O. Nowadays, there are tools like Web Dataset or LMDB, whatever you want, that allow you to have very fast read access. And so I always encourage people to use these kind of tools because it can help you to get the last 2-5% of speed on your training, especially when you go at scale. I'm not saying if you train Cypher, that is 50,000 small images, but maybe on bigger workloads, yes. Yeah, then say next part is you can take it as a sort of summary, and then based on what you would like to go deeper into, I can continue. So one thing I like to say to people is that the GPU is a quite big chip. It has a lot of cores inside that do many different things. This is a sort of schematic. So you have your CPU with the RAM of the laptop, for example, and you have a PCIe connection to the GPU. And then inside the GPU, there are the usual suspects, for example, like the VRAM, which is the one that gives you the out of memories that we saw before when I put the batch size too big, because it cannot store enough data. And there is the CUDA and Tensor cores. CUDA cores are more general purpose cores. Tensor cores are cores that do matrix multiplication, essentially. So they do the multiplication and addition in one clock. And then there are also other cores that you might think can be useful to your application. For example, in gaming or rendering GPUs like RTX something, there is the NV encoder and NV decoder. These are cores that decode or encode a video on the fly. So you load to the GPU the compressed video stream and decode it directly there. So you basically can use it without having to copy the full video back and forth. Then there is the NVJPEG that can allow you to load a JPEG image and decompress it directly there, or even optical flow. On the data center GPUs, the encoder doesn't exist because we think that you mostly use them to decode the video, not to really encode. Now, do you have to use them? This, for example, the NVIDIA decoder for the video depends. You might have a cluster or no compute nodes with very strong CPUs. So you might want to put that on the CPU and just use the GPU to train your model. Or you might have a bit weaker CPU and you can put everything on the GPU. We have libraries that can help you to do that, like the DALI data loading library, or another one that is called NVIDIA video codec. But yeah, it depends on the case. So after you know the GPU, if you have ever seen machine learning training or LLM training, there are a ton of things you can do to actually make it work, because typically they don't fit in your GPU memory. So you have to parallelize them and also to use tricks to make sure they can actually train effectively. Because it's always a balance game between networking and compute. So you always have this balance to strike. And typically in a good performance training, you have an utilization of the peak flops that the GPU can compute at around 45%. Like if you are training DeepSeek and you get a GPU utilization of around 45% of your cluster, then it means that you are doing a good job. Because there is also a lot of cost in networking around the cluster. So here I put a table and a list of techniques that you can use. There are some that help you to go faster and some that can help you to save memory. For example, gradient accumulation means that you are virtually creating a larger batch size. You can do that simply by doing forward and backward and not calling immediately the optimizer. You just accumulate the gradient and do the optimizer step at next time. There is gradient checkpointing, which means that you basically compute the activation for the next layer and then delete the previous one, so you save memory, but you will have to recompute this activation later to be able to compute the gradient in the backpropagation. There is mixed precision training that originally was, let's say, between FP32 and BF16. Now it's between FP8 and FP16, or even FP4, that you play around with it. There is the batch size that can allow us to process faster the dataset. And the optimizer is also quite important because I don't know if you ever checked, but for example, the Adam optimizer uses 12 bytes per weight. So it's a huge optimizer. You end up having more memory allocated for the optimizer than for the model and weights and everything. Data loader is something that I showed you in the example before. Is very important how we set it up. Optimizer can be distributed. The typical techniques used today are like the ones that Microsoft proposed, the zero optimizer, like 0, 1, 0, 2, 0, 3, depending how much you are distributing. Then there is offloading. Offloading means that maybe you use some weights to do computation, and then you copy them back to the CPU, to the RAM, and then you load them in the GPU only when you need. This is tricky on traditional HPC cluster like the Leonardo that I used before, but it can be worth to use, for example, in the GH or GB super chip of NVIDIA, because those chips have much faster bandwidth between CPU and GPU. It's at least one order of magnitude faster than the PCIe that normally you have. So maybe it's worth to try it. And these are things that you can do even if you use just one GPU. Then when you move to multiple GPUs, there is a ton of parallelization techniques that you can use, starting from data parallelism, which means that your model fits in one GPU, and you can just replicate it and run the training that way. The pipeline, which means that you are splitting some layers of the model on one GPU, some layers on another, or tensor. Tensor is particularly used for transformer models because they have big matrices to big linear layers. So from algebra, we know that we can split matrices and get the same results, even if we separate the two computation. And then the equivalent of tensor parallelism is sequence parallelism for other type of layer. So for example, for the dropout or non-linearities, you can use the sequence parallelism to keep splitting the flows of the model in different GPUs. And then context parallelism is useful to train models that have a very large context. So I don't know, this Llama 3.2 128K context. You need to be able to parallelize the sequence, so your sentence effectively into multiple GPUs, otherwise you would never be able to fit it. So these are a lot of techniques. I know that it's maybe hard to follow, but anyone that you want me to dig a bit deeper, just let me know and I can continue.
For the first one, data parallelism, since there's a replication among the GPUs, do we need a router or like load balancer, or is it taken care of by the library?
So we are lucky enough that the library takes care of it usually. But I can show you the detail. I have a slide that shows you a very easy schematic just to explain you how it works. Yeah, this one. We start with our data somewhere on the cluster. We suppose we have two GPUs just to make our life easier in explaining it. And the way it works is that you will, let's say here you start your data loaders. Here you allocate your model weights. Then when you do inference, you will allocate also your activations, which is, said it in a non-correctly way, it's simply multiplying data by weights of the model. You can allow me to say like that. Then you can compute your cost function. And bear in mind that these two guys will be different. So the weights are the same here and here. The activations are different because you started from different data. And then you compute the loss. The two loss will be different because you have different data. And then you need to start to backpropagate. So until this point, the two GPU or n GPUs that you are using or n replicas are independent. They just need to wait for data, process it, and come out with an output. And then here starts the part where you need to synchronize, let's say, the two processes, because you need to exchange the gradients and take an average. So you do a null reduce, I think, if I'm not confusing the words, before you can proceed to the next step. Because if you don't wait for this synchronization, you will have different gradients in the different replicas. You will not end up with the same model after the optimizer takes a step. So you keep going like this until you reach the end, and then your training iteration is finished. How this here is handled, there are algorithms that were developed to do this. I don't know them exactly. I don't remember how it's called, but it's implemented already in the library. For example, in PyTorch, there is a DDP package that handles all this distributed data parallelism that handles all this. And so let's say if you have a cluster with good networking, the NVIDIA gives you has already implemented the fact that all the GPU will communicate directly through this fast interconnect between each other without passing through the CPU and the normal Ethernet network, let's say.
An all reduce operation and some data. What are the data set sizes for this all reduce operations? What is the size of the input data? All reduce? Is it an error?
Depends on your model. It's usually tensors of gradients that you have to exchange. They depend on the model you're using. For example, I don't know, for a transformer model, you will have these tensor that are of the size of your linear projection layer, or I don't know, for convolution, they are the size of the activation that you computed with your convolution kernels.
Okay, so it can get large. It can also get large.
Yeah, it can get large. So it's a sort of problem because you have these bursts of traffic on the network, and yeah, so there are all sorts of complicated things under to keep it working.
You have this strong synchronization.
Perfect. So the protocol that they use to communicate is the NCCL, NCCL, that is an NVIDIA library to handle all this. Usually the infamous guy that gives you errors in NCCL that realizes that something is not working.
If you have many GPUs, you get a quite big effective batch size.
Yeah.
Can you recommend some optimized or learning rate scaling for that?
So let me check if I used to have a slide on this, but maybe not here. It's something that we know from quite a long time, let's say. Also in the ImageNet paper of Krzyzewski 2013 or so, he was saying when your batch gets bigger, like multiples of the original batch you had on one GPU, sorry. If you do the calculation of your expected, what was it? I don't remember. It's better if I don't say wrong stuff. But basically, he found out that you should multiply your learning rate by square root of the multiple. Like if your batch size initially was 100 and now you have 400, you should multiply your learning rate by square root of 4. But then in the paper, he also says, if you try just 4, it works even better. So I don't know if it's just the data set or what. So rule of thumb, your batch multiplies by n, you can multiply your learning rate by n. Why? Because the noise that is in the batch is actually less. So you need to help the model to maybe get unstuck from some local minima. Under the hood, I think in PyTorch, for example, there is some mechanism that help you with that to keep the model training stable and so on. But yeah, rule of thumb can be that. And then as optimizer, there are optimizer like Lars or Lark or I remember Novograd, something like that. They all basically play around the concept that you can either inject noise in the gradient or weight the gradients based on their magnitude or the activation magnitude. So they do some normalization of the weights for each layer. Do some normalization of the gradient for each layer, multiply by some constant, such that they inject enough noise to learn it effectively. But luckily, lately, we have so big models that is not so big a problem, the learning size. But
there's a question in the chat. I don't know if you should take this afterwards, but the question is, could you please explain a little bit more about pipeline and tensor parallelism?
Yes, we can. So with pipeline, we open a can of worms. So I go first to the tensor because it's easier. So tensor, let's say I put these slides have, where is my mouse? This slide has the image of the model, let's say, just to make you understand in which way we are parallelizing. If you do pipeline, you are parallelizing by layer. So in this case, is vertical line would be a vertical line. If you are parallelizing by tensor, you are parallelizing in the horizontal line here. So you're splitting the same layer on two different GPUs, for example. How does that work? You split the computation of matrices onto different chips, because otherwise they will not fit, for example. That's linear algebra, but there are two ways you can implement it. And like if you split both your input and your weights, or if you just split your weights and give the same inputs to both. Typically, you use this one on the right, because here you don't have to do much, you just replicate the data. So the forward pass goes on independently, then you collect them, and then you have your output. If you have a cascade of transformer, I also saw that they tend to mix them just to keep more balance between networking and compute. But in general, this one is used when you call tensor parallelism on your model. I mean, I don't think I have much more to say on tensor parallelism because essentially you just exploit linear algebra to make it work. It's relatively straightforward, more or less. I hope this, at least for tensor parallelism, helps. There are tons of blogs online that explain it probably better than what I can do. So I also invite you to give a look there if you want. And for the pipeline, so pipeline parallelism is essentially one of the ways you can parallelize your model. Here you see that with pipeline, we are basically splitting the model by layer. So for example, you have 6, you put 1, 2, 3, GPU 0, and 4, 5, 6 on GPU 1. How does that work? Is that we'll have your input here, you pass it to the GPU 0, it will process it and have some activations in output. And you will take those activations, move them to the GPU 1, and then process these again until you reach the output, and then you compute your loss, and then you go backwards in both the GPUs. So the problem that arises from this model parallelism is that you have bubbles, like a time where your GPU is not doing anything. If you see here, for example, this example, maybe it's easier to understand. You have GPU 1 processing the batch, then it passes the activation to 2, then to 3, then to 4, and then you start going backward. So all these times here, the gray, it's unused compute. Here is where the fun, let's say, starts. It's where people studied how to make this more efficient. There are many scheduling that were invented to make this work. The latest one, and the latest and greatest one, I think, is dual pipe from DeepSeek. But in between, there is a lot of them that came out over time. So the first and easiest one you can do is micro batching. So you can think, if you have a batch of 4 elements, you don't process the 4 elements at once, but you process one at a time. So you have this sort of flow that one be forwarded, the black can be perform the forward pass, and then you can perform the backward pass, the green one, then the second element, third element, fourth element. This is good, but still not optimal. It can be improved with some smart scheduling. And so you can do some interleaving between them. Why you do this interleaving? Because maybe it's not convenient to do immediately the forward and backward, but because you would have to wait for the data to be copied for the network. So you might delay some operation, hide them behind some other operation to have some overlap between compute and networking. And so still this is not ideal. We improved a lot, but still not ideal. So what can happen next is that you do more scheduling also between different batches of data. In that case, it starts to get more nicer. All the utilization training is more balanced. And last year, I also let me see if I can play it. But I can give you the link later to this. Here I also tried to, for personal study, to create this notebook where I explain this concept. I implemented myself a very simple model, and I checked how it changes between the vanilla pipelining and the micro batching, which is very easy to implement. Essentially, the vanilla one took 20 seconds. With the micro batching, you can see that I simply chunk the batch into pieces, and then do the inference over it. And in this case, it took 10 seconds just because I'm exploiting better the compute. I also profiled it, but now it doesn't show here. I need to search for the images. You also profiled it, and if you run the vanilla one, you can see that there is some utilization of the GPU, then it's idling, waiting for some memory transfer, and then so on. Instead, if you use micro batches, it's more or less always using the compute. And then I had also this the notebook. I had an overview of the techniques that I just tried to explain you. Where are they? Here, and like what it means, showing how you can actually compute the bubble time, so the time that your GPUs are idle. And also, yes, it had also explained a little bit dual pipe. Dual pipe is this technique like this. You can see it's very complicated. There are a lot of different colors, which means that there is at different times you are doing different things in a very precise way to exploit your hardware as much as possible. So for example, you can have forward, then start to do backward, then you do another piece of forward, then backward, or between all these, you are overlapping them too, and overlapping also with communication between the different GPUs. So it's quite complex. And to work well, they need, let's say, 8 GPUs, and they use 20 micro batches for this to work properly. There is also the version for 4 GPUs of it. It's called dual pipe V. If you have a cluster with 4 GPUs, you can use that. Yeah.
Can it happen that in the all reduce models are reduced together from different time steps of the training with that parallelism?
You didn't get the question.
Because you're updating different parts of the model at different times, more or less, and then you have to do all reduces in between.
I wouldn't say that you are updating at different times, because you are computing the forward pass and the backward pass in at different times, yes. But the optimizer step is triggered after all this, usually. So you basically compute your activation and your gradients.
Okay.
Once you're done with all this, you can trigger the optimizer step. So then you will end up your training iteration.
So this is just one iteration.
Yeah.
Okay.
It's just a very complicated way to try to keep things together. So I think this is more or less what I can say about lining. Well, then maybe to close it here, I have a slide of, let's say, guidance a little bit. Stating the obvious, you have to balance networking and computing, which techniques to use. So if you can, if your model is small enough, you start on one GPU and try to make sure that it works well there. Like have a good, smart way to store your data so that it's efficient to load. On some clusters, there are also different type of memory, like of hard disks. For example, the Cineca one has a fast partition and a scratch partition, so you might want to use them wisely. Data loader, maybe training low precision, so it's faster. Then when you go in multiple GPUs in distributed training, data parallelism is the easiest one. If it doesn't fit in memory, you can use smarter techniques for data parallelism like Zero or FSDP. After that, if it's not enough, you can start working with pipeline parallelism, and from there, it's you need always to customize for your workload. It's just a general, very general guidance. I wouldn't say take it with a grain of salt, let's say.
I've got a question in a different direction. Of course, energy consumption is an issue. What are typically use cases where power throttling will not have a big impact on training speed, for example? Because usually, if you're fully loaded to DGEM only, you do power capping, you will reduce performance by the same amount.
Yeah,
Did you investigate on that? So it might be when there's a good trade-off between reduced speed and saved energy.
Yeah, so I just heard that people are playing with it, but I don't know myself. So I don't have a good answer.
Okay.
I would say it would be nice to try to benchmark to see how you can if it's worth to maybe reduce 10%, if it's still you don't notice so much the difference, but maybe at the end of the month your bill is much less. Then I don't know. I don't have a good answer. I think it's because I come more from AI background than a system background, so I didn't really investigate that. Yes.
I have more like a discussion point. So I see all those different configs, right? So you can have means precision or the charting of the model, whatever. But when trying those, I often encountered it. Maybe it seems to work, but then I see problems coming up with the combination of the different techniques. I have to try again and again. It's almost like cooking. That's why I would like to see some more like cookbooks for our infrastructure that we can use for like the same model size, the same. Yeah.
Usually, so I don't know. When you do mixture of experts, it's a bit more complicated. But if you have a classic dense model, is relatively easy. You can, the world size, so how many GPUs you have available for your training, and then there is a formula that is like I think is how you parallelize the model. How many GPUs you need to parallelize the model depends on tensor parallelism that you do multiplied by data parallelism that you do. Then is there other stuff that I'm forgetting? Yeah, essentially you have to have that's the product of those guys is the same as your world size. Then maybe I'm forgetting stuff now. I don't remember.
Yeah.
If you search for this kind of formula, it might help you to compute in advance how many GPUs you need, so you don't have to try many combinations. But then what I end up doing very often is to try all this combination to see which one is the fastest, like the one that gives me the highest throughput on the cluster.
Yes, I tried every of those combinations, thousands of jobs.
I could show you a lot of Excel sheets where I have lists of parameters that I try and the throughput that I get from them.
But it would be good to have some understanding.
No, it's pretty. I think so. Let's say the rule of thumb can be the following. Tensor parallelism. So if you start from lowest to highest network in traffic, you have data parallelism that doesn't need too much communication. Then in the middle, you have pipeline parallelism. It's a lot more, but still okay. And then you have tensor parallelism that has a lot of communication. So if you start from this point, you would want tensor parallelism to be equal or smaller than your node size. So if you have 4 GPUs, like in my case before, you put TP maximum 4. Then pipeline parallelism, you do what you can based on your allocation of GPUs. And then data comes as a consequence of how much you can. Then nowadays, there are a lot of mixture of expert models. So there is one more variable, and expert is in between TP and PP. So typically, you try to maybe set tensor parallelism to 1 and use the expert parallelism to use your node. Then if you have a DGX node, it's easier because you have 8 GPUs in the same NVLink domain. If not, you do what you can.
And if you have money, you can even afford an NVL70.
Yeah.
But I have another question. So we will get quite some GB200 systems. And so far, we only worked on, not on Grace Hopper, but standard with Intel or AMD hosts.
Yeah.
This offloading could be of interest because we haven't had a look at that yet. So 2 questions. Do you also have some data loaders which do the communication with the DRAM, or is it transparent by uniform memory?
I mean, you can also think that the GB200 works the same as the other GPUs that you have, other systems you have.
Because they should also have a unified namespace.
Yeah. I've seen colleagues trying to do things with that, like trying to have part of the weights of the model on CPU and GPU. But I think the easiest option is to still use the GPU as best as you can, because it's 280 gigabytes of VRAM. So there is quite a lot. And maybe if you can, I would just copy the dataset RAM.
Because
So
this
it's
is
local.
my next concern. Usually you do those techniques only if the slow memory, the backup memory, is much larger than your fast memory. However, on GB200 or GB300, even worse, GB300, if you have 4 nodes, you have more GPU memory than host memory. So it's still under consideration how to use that.
Yeah, and for the software, we have a lot of containers that are ready to use also with PyTorch if you want to start from that, or JAX.
There's a question in the chat. Since you just mentioned mixture of experts training, what is the best practice you'd recommend to eliminate the communication bottlenecks like all-to-all?
I think I give wrong answer if I answer the question. I'm sorry. I'm also fighting with MOE lately. So
maybe a bit more of a hardware question. You showed a slide with the different components of a GPU, right? So you have this distribution of CUDA cores and these tensor cores. How does NVIDIA estimate the relationship of CUDA cores, which I assume are more universal, compared to these special tensor cores? I would assume you increase the fraction of the tensor cores on more high-focused GPUs.
Yeah, I think generally speaking, I know as much as you, and I think yes, your assumption is correct.
But for the end user, you cannot really estimate or optimize the usage of the tensor cores.
You need to be a very good CUDA programmer if you want to go into that.
Okay, so I have just to kind of pick the right precision, and the rest I have to hope works mostly on the tensor cores.
Yeah, basically the internally when you start your threads of computation, the GPU will take care of it, unless you really know you are able to program CUDA very well, and then you can take care of doing that. But I think it's extremely complicated to do that.
You have kind of a feeling how much the kind of utilization of these tensor cores compared to the CUDA stuff is, or?
Usually I don't dig so deep.
But that, at least that's something you don't have to, as a code writer.
It should be done for you by GPU.
You should look at, for example, when there's GP200 or GP300, like the 300 will have less FP64 tensor core, so you have to look which precision is actually on the tensor core.